Hi everybody. Okay, so in this module we're going to be looking at the representation of linear discrete time systems, and we're going to be looking at difference equations, transfer functions, all delay block diagrams, and state space models. So just to remind you where we are, in the previous modules we looked at various methods for representing continuous time plans, state space representation, all integrator block diagrams, and transfer functions. And then we introduced the models that describe the operation of the analog to digital converter and digital to analog converter. And what we want to look at in this module is this block in the middle, C of Z. Now C of Z, we call it the controller, the compensator, a filter. What we are interested in is how to represent this block. So again, in the previous modules we looked at the analog digital converter, we looked at the digital to analog converter, and what we are interested in today's module is the representation of this filter or controller or compensator C of Z. Okay, and again we're going to be looking at difference equations, transfer functions, we're going to be reviewing the Z transform, we're going to be looking at all delay block diagram, and then we're going to be looking at the state space representation. Okay, so let's start with the first representation, which is the difference equation representation. So if I have a linear time invariant discrete time system, that has an input u of k, notice that the input is discrete, and output y of k, also the output is discrete, then we can be represented by an nth order difference equation. And this difference equation is given by y of k plus n plus a n minus 1, y of k plus n minus 1 plus all the way to a1, y of k plus 1 plus a naught, y of k. This is k. And this is equal to bn multiplied by the input u of k plus n all the way to b1 u of k plus 1 plus b0 multiplied by u of k. This equation, we call it a difference equation. Now the time variable here is k, and n is a fixed integer that we call the order of the difference equation. N is a fixed integer that is called the order of the difference equation. Okay, now in order to solve this difference equation for y of k when k is greater than n, in addition to the input u of k, we also need initial conditions. So in order to solve the difference equation, in addition to knowing the input, we also need initial conditions. And these initial conditions are going to be y of 0, y of 1, all the way to y of n minus 1. So again, this is an nth order, so therefore we're going to have initial conditions from 0 all the way to n minus 1. So let's look at an example. So if I have a third order difference equation, I'm going to have, as an example, y of k plus 3 plus a2 multiplied by y of k plus 2 plus a1 y of k plus 1 plus a0 y of k equal to b0 multiplied by u of k. And again, remember, there is no initial conditions for the input. The initial conditions are only at the output because the input is known. Okay, so in this case, what are the initial conditions that we're going to need? We need initial conditions that are y of 0, y of 1, and y of 2. Why? Because if I want to calculate, for instance, the output when k is equal to 0, so I want to calculate y of 3. Y of 3 is equal to negative a2 multiplied by y of 2 plus, minus a1 multiplied by y of 1 minus a0 multiplied by y of 0 plus b0 multiplied by u of 0. Now u of 0 should be known because it is the input that I'm trying to calculate the output for. But when I calculate, in order for me to calculate y at 3, I'm going to need y of 2, and I'm going to need y of 1, or y at 1, and I'm going to need y of 0. These are given as initial conditions. Now when I calculate other outputs, I might need the initial conditions, or I might need the output that I calculated from previous calculations. Okay. So again, for this system, I know y of 0, I know y of 1, I know y of 2. I'm going to calculate y of 3. I'm going to need y of 0, y of 1, and y of 2 in order to be able to calculate y of 3. The second representation is the transfer function. Now also, before we talk about transfer function, you can see there is similarity between the difference equation and the differential equation with the continuous time system. The second representation is using a transfer function. Now, in order to get the transfer function representation, we're going to be introducing a very important tool for the analysis and the design of sample data system, and that is the Z-transform. So this is a tool for analysis and design of sample data system. Now I imagine most of you are familiar with the Z-transform. You've seen in previous classes. If you're not familiar and you need help with it, please let me know. I can point you to references or the lectures that we have from Signals and System or Digital Signal Processing, and you can watch it to come up to speed to it. Now, what is the role of this Z-transform? The Z-transform is similar to the Laplace transform in continuous time system. Similar to Laplace transform in continuous time systems. Okay, and remember the Laplace transform, we took a differential equation, we apply the Laplace transform to get the transfer function. Similarly here, we're going to be using the Z transform, we're going to apply it to a difference equation in order to get the transfer function. How do we define this Z transform? What we're going to be using is a one-sided Z transform. We use the one-sided Z transform. What does that mean? The Z transform is defined as y of z equal the Z transform of y of k, and this is equal the summation from k equals 0 to infinity y of k z to negative k. We call this the one-sided Z transform. Why do we call it one-sided Z transform? Because we start with k equal to 0. So the Z transform only takes y of k when k is greater or equal to 0 when we're calculating y of z. Unlike the two-sided Z transform, where we have the summation from negative infinity to infinity, the one-sided Z transform, we start the summation from k equal to 0. So this is equivalent if I were to take the two-sided Z transform, if I take the signal and multiply it by u of k and calculate the two-sided Z transform, I'm going to get the same results. Does that make sense? So what I'm saying basically, if I have a signal and this signal is two-sided, so the signal looks something like this. This is 0, 1, 2, negative 1, etc. If I multiply this signal by u of k, the unit step function, this is u of k starting from 0, what I'm gonna get is only the signal when k is greater than or equal to 0. So I'm gonna get the signal when k is greater than or equal to 0. If I calculate, if this is x of k, if I calculate the two-sided Z transform of x of k multiplied by u of k, I'm gonna get the same result as the one-sided Z transform, because when I multiply it by u of k, everything that was before k equal to 0 is gonna become a 0, and that is equivalent as if I were to take the summation from 0. Okay, what is this Z? If you remember, the Z is a complex number, and therefore we can write Z as equal e to e multiplied by e to j theta, which is equal to r cosine theta plus j r sine theta. Now also this is similar to S in the S domain that we used with the Laplace was a complex variable. We could write it as sigma plus j omega. So similar to how S is a complex number, Z is also a complex number. Has a real part and imaginary part. And if you remember, Z was equal to e to S multiplied by t. So the relationship between Z and S is that Z is equal to e to S multiplied by t. Okay, so let's look at some properties of this Z transform. So the first property is the addition and subtraction. And what this says, if I have two signals f of k plus or minus g of k, and I want to take the Z transform for them, of course this simple Z represents Z, this is going to equal the Z transform of the first signal plus or minus the Z transform of the second signal. The second property is multiplication by a constant. And that if I take the Z transform of alpha multiplied by f of k, this is going to equal to alpha multiplied by f of z. Now if I look at these two properties, then it shows that the Z transform, if I look at property 1 and property 2, it satisfies the superposition property. And therefore, the Z transform is a linear operation. We can write that the Z transform of alpha multiplied by f of k plus beta multiplied by g of k is equal to alpha multiplied by f of z plus beta multiplied by g of z. Okay. Another property is the real translation or shifting. And what this property says, if we advance y of k by n steps, y of k, this is k, by n steps, then the Z transform of e, let's make it e, let's keep it y of k plus n is going to equal to z to n multiplied by y of z minus z to n y of 0 minus z to n minus 1 y of 1 all the way to minus z y of n minus 1. So if I shift the signal to the left, then I'm going to be removing from the shifted signal all these terms. Now to illustrate this, let's look at what happens for a one-step advance. So if I shifted the signal to the left, z of e of k plus 1 is going to equal to z multiplied by e of z minus z multiplied by e of 0. What does that mean? I mean, this might be a little bit confusing. So let's illustrate it with an example. And if you understand the example, you would understand the concept we're trying to discuss. So let's look at a very simple signal. So let's say we have a signal that is very simple. Just the signal is a 1 at 0, and it is equal to a 2 at 1. Let's call this signal x of k. Now if I calculate the Z transform for x of k, from the definition is equal the summation from k equals 0 to infinity x of k z to negative k. And therefore x of z is going to equal, when k is equal to 0, x of 0 is equal to a 1 multiplied by z to 0 plus when k is equal to 1, x of k is equal to 2 This is x of k, and therefore plus 2 multiplied by z to negative 1. So therefore this is going to equal to 1 plus 2 multiplied by z to negative 1. Agree? Now what happens if I shifted this signal to the left? So what I'm going to do, I'm going to take this signal, I'm going to plot x of k plus 1. What is x of k plus 1 going to look like? This is going to shift the signal to the left. I'm going to have the 2 here at 0, and the 1 is going to be here. Negative 1 is going to have a 1. Agree? Now if I'm going to calculate x of d for this signal, let's call this x2 of k, which is equal to x of k plus 1. So x2 of z is going to equal the same thing, the summation from k equals 0 to infinity x2 of k multiplied by z to negative k. Agree? Now what is this going to equal to? It's going to equal to x2 at 0 is equal to a 2 multiplied by z to negative 0, and that's it. This term here will not show up in the calculation. Why? Because I'm taking the one-sided z transform, and therefore I'm taking from k equal to 0. So therefore, what is this going to equal to? This is just going to equal to a 2. Now how is this result compared to this results? I can see that if I take the results that I got here, and if I multiply it by z and subtract from it z multiplied y of 0, I'm gonna get this, the result I got in the second signal. What does that mean? So what I'm saying is the property is that z of x of k plus 1 is equal to z multiplied by x of k minus z multiplied by x of 0. So therefore, if I want to calculate it, I calculated x2, which is x of k plus 1, using the definition. But if I use this property, what is this going to equal to? It's going to equal to z multiplied by x of k, x of z. Sorry, this is x of z. What is x of z? From this expression here is 1 plus 2 multiplied by z to negative 1 minus z multiplied by x of 0, which is equal to a 1 multiplied by 1. What is that equal to? This is going to equal to a z plus 2, z multiplied by z to negative 1 is going to give me just a 2 minus z, and this is equal to z with z is going to cancel, just equal to a 2, which is what I got in here. This and this are the same. Is this clear? So basically what we're saying is, if I shift the signal to the left, all the terms that are gonna shifted before 0 are not gonna be in the calculation of x of z. So therefore, if I have the original signal like this, I calculated x of z, then I shifted it to the left, I have to remove all the terms that went before, that are shifted before k equal to 0, because they're not gonna be in the calculation of x of z, because I'm taking the one-sided x of z. Okay, so that is what happens if I shift the signal to the left. Now if I delay the signal, e of k by n steps, if I shift the signal to the right, then the z transform of e to k minus n is going to equal z to negative n multiplied by e of z. And if I were to do a one step, so if n is equal to 1, for a one step shift or delay, I'm going to get z of e of k minus 1 is going to equal to z to negative 1 multiplied by e of k. Again, let's do a quick example, just show that. So let's take our signal that we just had before, x of k, and x of k was 1 here and a 2 here, 0, 1. This is x of k. So x of z we said was equal to a 1 plus 2 multiplied by z to negative 1. Now what happens if I shifted this signal x of k by 2? It's shifted by 2, not by 1. What's going to happen? This is 0, 1, 2, and 3. This is going to come here. This is going to be the 1, and at 3, this is going to be the 2. This is the signal if I shifted by 2. What is x of z? According to the definition, x of z is going to equal to the 1 multiplied by z to negative 2 plus the 2 multiplied by z to negative 3. Again, this follows directly from the definition of x of z. X of z is the summation from k equals 0 to infinity x of k z to negative k. So here I have k equal to a 2, x of 2 is a 1 multiplied by z to negative k, z to negative 2. X when k is equal to 3, x of 3 is equal to a 2, which is this 2, multiplied by z to negative k, and k is 3, z to negative 3. Now if I compare this x of z that I got for the shifted signal and x of z, the original signal, what do I notice? If I take this signal, this x of z, and multiply it by z to negative 2, I'm gonna get this x of z. So therefore, if I shift the signal to the right by 1, I will multiply by z to negative 1. If I shift it to the right by 2, I'm gonna multiply x of z by z to negative 2, and so on and so forth. In general, if I shift the signal to the right by n, then the z transform of the shifted signal is going to be z to negative n multiplied by the original z transform of the signal. Okay. Another property is the initial value theorem. And what the theorem says, e of 0 is going to equal to the limit as magnitude of z goes to infinity of f of z if the limit exists. Always with these limit properties, we say if the limit exists. Another property is the final value theorem, and in this theorem, if the poles of z minus 1 multiplied by f of z are inside the unit circle, then the limit as k goes to infinity of e of k is going to equal to the limit z goes to 1 of z minus 1 multiplied by e of z. Now, since we are just reviewing the Z transform, we'll try to practice the Z transform with the homework. So in the homework assignment, we're going to be looking at these properties and trying to practice them. Again, the assumption is most of you are familiar with the Z transform. You just might need to brush up on it and refresh on it. Okay. So with that, let's do an example where we want to calculate the transfer function from a difference equation. So what we want to do is we want to find the transfer function So we have a difference equation, y of k plus 2 plus a1 y of k plus 1 plus a0 y of k equal to b0 multiplied by u of k. How do we find the transfer function? To find the transfer function, we're going to take the Laplace transform from both sides. We're going to take z transform of both sides. So if I take the z transform of y of k plus 2, I'm going to get z squared multiplied by y of z plus a1 multiplied by z Actually, let's also put the initial conditions just so the example is complete, but we'll see what we will do with the initial conditions. So y of k plus 2 from the property of the shift is going to equal z squared multiplied by y of z minus z squared y of 0. This is small letter because it's in the time domain. Y of 0 minus z to the 1 y of 1 plus z multiplied by a1 y of z minus z multiplied by a1 y of 0 plus a0 multiplied by y of z, and this is going to equal to b0 multiplied by u of z. Similar to what we've done with the continuous time domain, in order to get the transfer function, we set the initial conditions to 0. So set initial conditions to 0. And then we solve for y of z divided by u of z. So all these initial conditions that I wrote here, I'm just gonna set them to 0. And therefore, I'm gonna also solve for y of z over u of z. If I take y of z as a common factor, I'm gonna get z squared plus a1 multiplied by z plus a0, and this is gonna equal to b0 multiplied by u of z. Then I can take y of z divided by u of z, and this is going to equal to b0 divided by z squared plus a1 multiplied by z plus a0. So this is the transfer function, and that is how we obtain it from a difference equation. We take the z transform, we set the initial conditions to 0, and then we factor y of z divided by u of z. Okay. Now let's just look at some used z transform, frequently used z transform. Now there is a table in the book in that will have the Z transform table. Now, one of the very common Z transform that we're going to be using are the following. So I'm going to just put them in a box here. The first one, the sequence and the Z transform. A unit step function, which is u0 of k equal to 1 when k is greater than or equal to 0 and 0 otherwise. What is the Z transform of u0 of k? It's going to equal to Z divided by Z minus 1. Now, although I should be consistent, sometimes I'm writing the Z with a tail, sometimes I'm not, but both of them are the same. Another common signal is A to K, and the Z transform is Z, let me be consistent, Z divided by Z minus A. Another is K multiplied by A to K, and this is the Z transform A multiplied by Z divided by Z minus A squared. Okay. So let me stop this module here and we'll continue on the next module. And let's refer to this as a C commonly used Z transform pairs.